All right, so this problem number 15, I'll start with this one. And this is the one where instead of the object being located at the high point, 12 o'clock, or the low point, 6 o'clock, or even the midpoint, 3 or 9 o'clock, we're talking about when the object is either located somewhere in here, somewhere in here, somewhere in here, or somewhere in here. And actually, when you're doing it, it doesn't really matter whether, like if I say, well, let's read the problem and I'll get started with this. So it says that a small body of mass 0.12 kilograms swings in a vertical circle. So vertical circle, like you make it look like a circle, at the end of a cord of length 1.4 meters. If its speed is 5 meters per second when the cord makes an angle of 34 degrees with, now this is what's important, with the upper half of the vertical. So that's going to determine what the picture is going to look like. The upper half of the vertical is going to be from 12 o'clock to the center of the circle. That's the upper half of the vertical. The lower half of the vertical would be from the center of the circle to 6 o'clock. So the angle between the string and that line that I just drew, that's where I'm going to label the angle. So I'm going to have that the angle, 34 degrees, would be something like that. And it's a small mass, so I'm just going to say there's my small mass at that location. Now, it says 34 degrees, but I'm just going to list it generically as theta right now. So I'm going to call that theta. Now, I want to put the forces that are acting on that object when it's in that position. And I'm going to have the weight of the object, which is going to be straight down. And I'm going to have the tension that's in the string. And the tension in the string is always towards the center of the circle. You could have the normal force away from the center, but you cannot have the tension away from the circle. The tension is that if I cut the cord, if I cut the string, it's going to move in a straight line and move away from the center of that circle. So in drawing that, we're going to have the tension is going to be along the line of the string. So I'm going to make it like that. So that, I'm going to label it over here. That's your tension. Now, the weight then now has to be broken into its centripetal and tangential components, because the way the weight is right now, it's not in either one of those directions. Now, the centripetal direction is along the line from the center of the circle out. That's your centripetal direction. The tangent direction is tangent to the curve. It's perpendicular to the centripetal direction. So what I'm going to do is I'm going to take that weight and I'm going to break it into its component that is centripetal, which is right along the same line as the tension. And let me draw that line again. So that's my centripetal component of the weight. And notice how far down I drew it. I drew it so that I can then go at a right angle to that and end up at the end of this line. So don't make this go all the way down here and then over. The weight is the hypotenuse of the triangle. This is the centripetal component, and then the arrow here will be the tangential component. There has to be a right angle between these two. So I'm going to have the tangential component will look like that. Now, labeling all these, let me label the weight is on this side. The centripetal component of the weight is on that side. And the tangential component of the weight is on this side. So there is your picture. Now, I told you that in most of these problems, we're not solving for tangential acceleration, because we usually do these problems and we call it uniform circular motion, which means that the object is moving at a constant speed. This problem is different because there is a tangential component of force on the object, so there's going to be a tangential acceleration. So at that moment in time, the object will have an acceleration that's causing the object to speed up, in addition to an acceleration that's causing it to change direction. So when I sum up my forces in the centripetal direction, I have both of my forces are towards the center of the circle, so both of them are positive. So you're going to have T plus W, and that always equals MA. When you sum up your forces, they always equal MA. But when we do a circular motion problem, we use for A either V squared over R or R omega squared, depending on what the unknown is. The unknown in this problem is not the radius, and they didn't give me the angle in radians per second, so I'm going to set this equal to mv squared over r. So that's my equation. That's my centripetal force equation. Now I can simplify. Hold on 1 second. I'm missing. That's my centripetal force equation with the C, because it's not the weight in the T. It's the weight. It's the centripetal component of the weight and the tension that together change the direction of the object at that location. So I'm going to replace to simplify this equation, I am going to replace WC with, if we look at the picture, WC is over here. If we know the angle here, then we also know the angle there. Both of those angles are both going to be the same thing. So that angle right there is going to be theta. And I know that because that's a vertical line, the weight is vertical, and that's a vertical line. So these two lines are parallel to each other. Well, if I have a line that goes from one to the other, then alternate interior angles are congruent. So if that's theta, then that's theta in the problem. And if you look, if this is the hypotenuse of the triangle, and that's my angle, that's the adjacent side. So what I'm going to do is I'm going to replace WC with W cosine theta. But W is mg, so I'm going to replace it further. I'm not going to put W cosine theta. I'm going to put mg. Oops. I'm going to put mg cosine theta equals mv squared over r. All right, so that's my centripetal force equation. Now, if I read the choice, the questions that they're asking, the first question is find the tangential component of acceleration. So in order to find the tangential acceleration, I need the tangential force. So I'm actually going to also sum up my forces that are tangential. So when I sum them up, there's only one blue arrow on my picture. So there's only one force that's tangential, and that's the tangential component of the weight. Now, just like I just said for the other one, anytime you sum up your forces, they equal ma. Newton's second law, F equals ma. So this also equals ma. But I'm going to write it as ma, but since the forces I'm adding up are tangential forces, then it's going to cause a tangential acceleration. And so to get the answer for part A, I'm just going to rearrange the equation to solve for the tangential acceleration. So Wt divided by m. Now, just like what I did up here, where I replaced Wc with mg cosine theta, I'm going to replace Wt with mg. We look at the picture here. Wt is the opposite side from the angle. So if Wc is mg times the cosine of theta, then I know that Wt is mg times the sine of theta. And I'm dividing that by m. So you can see here the m's actually cancel out, and the answer is going to be, for the tangential acceleration, g times the sine of the angle. Now, one thing that I will say about this problem is if you look at the picture, when the object is here, the weight's straight down. So when it's at 12 o'clock, the weight doesn't have a tangential component. So the tangential acceleration right here would be 0. As it moves here, we're now going to start getting a tangential component. When I get to 3 o'clock, all of the weight is in the tangential direction at 3 o'clock, because straight down is tangent to the curve at 3. So I know that at 3 o'clock, my acceleration will actually be 9.8 meters per second squared. So it goes from 0 to 9.8. So this is somewhere in between. So I better get an answer here that's somewhere between 0 and 9.8. You can even see it from the equation, g sine theta. The only sine theta has to be a number between 0 and 1. When it's 0, then the acceleration is 0, because 0 times anything is 0. When it's 1, it's equal to g, which is 9.8 meters per second squared. So solving that, let's just put in the numbers. So AT is going to equal 9.8 meters per second squared times the sine of 34 degrees. And that's it. And that came out to be, what did that come out to be? 5.48 meters per second squared. So I should do all my podcasts with your class, because the other class, I asked the same question and it took like at least a minute for me to get an answer there. And I'm wasting podcast time when I'm waiting a minute just to get that answer. And if they did the homework, then I would hope that somebody in the class would have got that answer. So there's your answer for part A. And now in part B, we're looking for the tension. We'll look at the picture. We have it up here where we're looking for tension. And all I have to do is move that to the other side and plug in all the numbers. And I don't even have to do a conversion in this problem because they literally gave me the velocity. So, a lot of times you have to, they give me the revolutions per second or the time per revolution. I have to convert it, but all the numbers are all in the problem. There's the mass, there's the R, there's the V. So all I have to do is plug it into this equation after I've moved this term over there. So the answer for part B, I'm going to get I'm going to get T equals mv squared over r minus mg cosine theta. So if we plug in the numbers, mv squared over r minus mg cosine of 34 degrees. So the m, what was the m in the problem? 0.12, so that goes there, and that goes there. While I'm over here, I know gravity is 9.8 meters per second squared. The velocity was 5 meters per second, and what was the R? 1.4. And if you put all those numbers in, what do you get for your T? What was it? 1.17 newtons. Any questions with that? So I'm going to give you another one here. Maybe I'll have it in the bottom half for the other one. So the key is when they say the angle will always be formed with either the upper half of the vertical or the lower half of the vertical, right, when you're doing this. And somebody in the other class asked me, they said, well, could I have done it over here instead of over there? Yeah, as long as the angle is 34 degrees between the string and the upper half of the vertical, it doesn't have to be done to the right of the upper half of the vertical. It could be done on the left side.